All right, so picking up with lesson 2, using the fundamental theorem of calculus, these examples are going to show or apply the fundamental theorem of calculus. So here we've got the area of the region between the curve y equals 4 minus x squared. X is between 0 and 3, and the x-axis. So I've provided what this region looks like. We have 4 minus x squared, which is a quadratic that opens down, which is this right here. We're binding that region between 0 to 3. So here's 0, here's 3, and so we also are binding it by the x-axis as well. So we have part of the curve, or part of the region, or the region above the x-axis, and this portion of the region is below the x-axis. So if we want to find total area, area has to be positive. We know this area is going to be positive. This area is going to be negative because it's below the x-axis. So to find the total area, we're going to need to write an expression for the total area in terms of a sum of two integrals. So notice that this region goes from 0 to 2, and this region goes from 2 to 3. So here's what our region is going to look like. Not our region, but this is what our expression is going to look like. To find the area, we will evaluate the integral of 4 minus x squared dx from 0 to 2. Now, because we know that this area right here, this value will be negative, we're going to negate that with a minus, so we can force this area right here to be positive. So we will find, integrate 4 minus x squared dx and evaluate it from 2 to 3. So here's what that might look like. Setting this up, the antiderivative of 4 is 4x, minus the antiderivative of x squared is x cubed over 3. We will evaluate that from 0 to 2. We will subtract, and we have the same antiderivative, and we will evaluate this from 2 to 3. Now, I like to do this. When I have the sum or difference of 2, I like to really separate the two expressions with brackets. It's not really necessary, but you have to always be careful when you're subtracting. So, I know I've got the antiderivative here and here. I know I need to evaluate this at 0, 2, and 3. So I'm just going to kind of come over to the side maybe and do some evaluating. So let's see. So I have 4, I'm going to start with 0. 4 times 0 minus 0 cubed over 3. Luckily, that just turns out to be 0. And then I need to do substitute 2. So 4 times 2 minus 2 cubed over 3. 2 cubed over 3 is 8. So I have 8 minus 8 thirds, which is going to be 24 thirds. Minus 8 thirds is 16 thirds. And then I need to substitute 3. So 4 times 3 minus 3 cubed over 3. That's 12 minus 27 thirds. And that will be 36 thirds. And 36 minus 27. What's 36 minus 27? I've just totally drawn a blank. um, let's see. 36. I have to look at it. 36 minus 9, isn't it? 27. 16 minus, yeah, that's 9. So that turns out to be 9/3, which is 3. Sorry about that. 4 times 3, 12. 3 cubed is 27. And I guess, well, that was dumb on my part. 27 over 3 is 9. 12, the subtraction would have been a whole lot easier. 12 minus 9 would be 3. So I just had a little brain freeze there for a minute. So I've got everything I need. So this is what it's going to look like. So I evaluate this at 2, and that value was 16/3, minus substituting 0, which was 0, minus substituting 3, we ended up with 3, minus the expression at 2, which was 16/3. So let's see what we end up with. So we have 16/3 minus, okay, I need to do a little work here. 9/3, 9 minus 16 is -7/3. And so we end up with 16/3 plus 7/3, which is going to be 23/3. So the area, the combined area between 0 to 2 and 2 to 3 is going to be a positive 23/3, which is approximately 7.667-ish, something along those lines. But because part of this area, or because part of the region was below the x-axis, we have to negate that when we want to find the area under that is bound by those two curves. Okay, so now let's talk about this example. It says find the total area of the region between the curve of y equals cosine of x, the x-axis, and the x-axis between 0 and 3 pi over 2. Okay, well, I want us to be reminded, I want us to remember what the graph of cosine of x looks like. So cosine, remember the normal period for cosine is 2 pi. If we divide that into 4 equal parts, this is pi over 2, this is pi, this is 3 pi over 2. And cosine starts at 1, and then it's 0, -1, 0, and 1. So the graph of cosine looks like this. But we want the total area of the region that is bound by this curve, the x-axis, and 0 to 3 pi over 2. So this is the area that we're interested in. Okay? We're not interested in this portion right here because that's greater than 2 pi. So we want to first write an expression that represents the area of that region, and because a portion of the region is above the x-axis and a portion is below, we're going to need to write the expression as the sum or difference of two integrals. So the first will be the function cosine of x dx from 0 to pi over 2. Because this next portion is under the graph or under the x-axis, we need to negate that. And this portion goes from pi over 2 to 3 pi over 2. And that is also cosine of x dx. All right, so now we're ready to find the antiderivative. The antiderivative of cosine of x is sine of x, and I will evaluate this sine of x from 0 to pi over 2, minus sine of x evaluated from pi over 2 to 3 pi over 2. So, when I evaluate, this is what I'm going to get. Sine of pi over 2 minus the sine of 0, that's this portion, minus the sine of 3 pi over 2, minus the sine of pi over 2. And then when I clean this up, sine of pi over 2 is sine of pi over 2, sine of pi over 2, 0, 1. Sine of pi over 2 is 1. Sine of 0 is 0. So I've got 1 minus 0 minus sine of 3 pi over 2, 0, negative 1. Negative 1 minus the sine of pi over 2 is 1. And so here we have 1 minus negative 2, which turns out to be 3. So the combined area is going to be 3. So why can we not just write this integral from 0 to 3 pi over 2? Because what's going to happen is it's going to, if you write it this way, it's going to take this area and add this area, and because this area is negative, your value will be something totally different. So you kind of have to be careful about that. When it says find the total area, you need to figure out, is the region above the x-axis, is the region below the x-axis? So knowing how a graph behaves is really, really, really helpful. Okay, so now let's talk about applying and using the second part of the fundamental theorem of calculus. Okay, so here we have the graph of a continuous function f that is defined with a domain 0 to 8. So we go from 0, we go to 8. Now I'm introducing another variable, h. Let h be the function defined by h of x equals the integral of f of t dt from 1 to x. Okay? So just to kind of give us some a heads up, we know we're going to need to find h of 1. I'm going to want to know, is h of 0 positive or negative? Find the value of x for which h of x is a maximum. Find all the coordinates, x coordinates of the points of inflection of the graph of h, and then find the value of x for which h of x is a minimum. Okay, so let's look at this function. We are told that this graph is the function f. Okay, so this is function f, and which is like y equals f of x. So this is f of x. All right, so I want us to go and let's look at what we are told that h of x is. We are told that h of x is the integral of f of t dt from 1 to x. Now, this looks familiar. Because I'm seeing a lower bound of something like 1 and an upper bound of x, what this tells me is that I can actually get some information about h prime of x. Okay, let's talk about what h prime of x would be. If I wanted to find h prime of x, remember I would do just differentiate both sides of the equation, and the derivative of h of x is h prime of x. And remember, when you're derivating, when you are finding the derivative of an integral and the upper bound is a variable, there's not a whole lot of work to be done. The second part of the fundamental theorem of calculus simply says replace t with that upper limit, and we get f of x dx. So now I know what h is. H represents this, and h prime represents f of x. Well, guess what? This graph represents f of x, and I don't need that dx on there. So I have a function that is f, but I can also name this as h prime of x. So this graph represents f of x, which could also be named the derivative of h. Okay, so, all right, so let's take a look at what we are asked to find. So the first thing we're asked to find is h of 1. All right, well, what do I know about h? Well, I know h is defined as the integral from 1 to x. Well, what is x? X here is 1 of f of t dt. Okay, well, we still have this f of t dt business, but I want us to just really consider this for a minute. What should the value of h of 1 be? Regardless of what this function is here, when you find its antiderivative and you substitute the upper bound of 1 and you substitute the lower bound of 1 and you subtract, you should and will get 0. Okay? Okay, now let's talk about h of 0. So, once again, h of 0 is what I want to address. So, what does h of 0 look like? Well, if I go back to what h of x is defined as, I go from 1 to 0 of f of t dt. Well, okay, we got a problem with the 1 and the 0. If you recall, we can fix that by switching the 0 and the 1 by pulling out, or multiplying, I guess, by a negative. So doing this allows me to switch my 0 and 1. And now let's talk about this. How do we find h of 0? Well, the good thing is that we're not supposed to find a specific value. What we want to know is h of 0 positive or negative. Okay, so let's talk about what we found here. We know that h of 1 was equal to 0. So it makes sense that h of 0 would be less than 0 because the negative out front. Okay, so if you look at this, h of 0, if this represents h prime of x, how would I go about evaluating h of 0? Well, if this is h prime of x, and I switch this around to be 0 to 1, the area under the curve from the graph is positive. But the only way we could get this is that we had to multiply by -1, which then is going to force the area here to be negative. So therefore, h of 0 is going to be less than 0. So h of 0 is less than 0 because of the integral of 1 to 1 of f of t dt was equal to 0. So this kind of thing, you kind of have to really think through and process it. All right, so now moving on to the next, it says find the value of x for which h of x is a maximum. So now what we have to remember is this: a maximum occurs where h prime, its derivative, changes from positive to negative. Okay, so h prime has to change from positive to negative. So if we look at our graph, on the interval 0 to 8, where does h prime change from positive to negative? And that would occur here at 4. So x equals 4 is where h of x has a maximum. So that means h of x, of course, would change directions from increasing to decreasing at x equals 4. Okay, then it says to find all the x coordinates of all points of inflections of the graph of h. Okay, looking at this graph and knowing that this graph represents f, which can also be described as the graph of h prime. This graph represents h prime. If I want information about a point of inflection, that has to be you get that from the derivative of the derivative. So h double prime is kind of what I'm thinking in terms. Well, how do I know where the point of inflection will occur from a graph of h prime? Well, that's going to occur wherever h prime equals 0. Okay, so h prime has to equal 0 in order for the original h to have a point of inflection. So h will have a point of inflection, which means it changes concavity at x equals 0. And I know that because the derivative of the derivative is h prime. And so I have to know where h prime equals 0. I lied. No, not where it equals 0. I need to know where this is going to be not where h prime equals 0. I'm so sorry. This is going to be where h prime has a maximum or a minimum. This is all the coordinates for all the points of inflections for the graph of h is going to occur where the second derivative equals 0. Well, how do you determine where h double prime, the second derivative, equals 0 from the first derivative? Well, that would be at the maximum and the minimum of the h prime graph. So we have a minimum there and a maximum at 3 and then another minimum at 6. The slopes of the tangent lines are 0 at 1, 3, and 6. So that means that the second derivative equals 0 at those 3 values. So that's going to occur at x equals 1, x equals 3, and x equals 6. You really have to, it's one of those things where you really have to process and identify and figure out what you're given and what you're trying to find. Okay, and then lastly, this last question says, find the value of x. So I'm looking for one value where x of x for which h of x is a minimum. Okay, so I need to find the x value where h of x is a minimum. So h of x can be a minimum at either the endpoints, x equals 0, x equals 8, and let's think about if there's an interior point where h prime changes from negative to positive. In order for h of x to have a minimum, h prime would have to change from negative to positive. And there is nowhere on this graph or for the function on 0 to 8 where the derivative of h changes from negative to positive. So our minimum is either going to occur at x equals 0 or at x equals 8. Okay, so now let's think about this. What did we find h of 0 to be? Or did we? Well, what we said h of 0 is we knew that h of 0 would be negative because we had to negate this area. Well, what if we were to just estimate, and I've drawn all over this graph, but what if we were to estimate the area, on this graph from 0 to 1? We're looking at something like this. Well, if we were to think about this as a triangle, and that being 1, we know that that value would be, h of 0 would be approximately negative, let's say a half. Okay, and then let's compare h of 8. So h of 8 is going to be, because again, we want to know we want to know the x value for which h of x is a minimum. So I'm going to evaluate h at 8. And so what that gives me, or what that looks like, would be 1 to 8, a f of t dt. Okay, so from 1 to 8, we know from 0 to 1, that value is negative 1/2. Then from 1 to 8, let's look at our areas. Well, 1 to 4. 1 to 4 is going to be a positive, and then from 4 to 8 is going to be negative, and the amount of area from 4 to 8 is negative. This area is negative, and combined, those negative areas is a larger value of negative area than this would be, positive area. Okay, so what does that mean? That means that h has a minimum at x equals 8. All right, so this is how using the fundamental theorem of calculus looks in terms of finding or utilizing it in problems. So when you're given a graph, I highly recommend that you always look at it and ask yourself, what does that graph represent? Okay, and then what does it represent in different forms? So for this one, you had that this graph, we were told, was the graph of a function f, And then we were given information about another function, h, and if we found the derivative of h, we found that the derivative of h turned out to be exactly f of x, which is what we have here. And so since this is named f of x, we could also label it or name it h prime of x, because those two things are the same. And then all of my questions were all about h, not f. Okay? So, it's kind of crazy, but that is what the fundamental theorem of calculus actually looks like. Okay? All right. Awesome.